Wednesday morning.
So this lecture was supposed to be tutorial one, but I thought I will finish my lecture and then on Wednesday morning I will present a tutorial. While listening to this lecture, I realized that he has covered many things that I wanted to cover in this lecture. So let's take up some of those things that he is introduced in little more detail. Okay. So these told you how to calculate X alpha, that is Lyman alpha coupling coefficient. And the formula, the equation by which you can actually calculate Lyman alpha coupling coefficient can be written as this 16 So all quantities except these are known, kind of constants. So this is T gamma, this is T also known. So this is J alpha, is Lyman alpha flux. And in order to calculate X alpha, that is Lyman alpha coupling coefficient, we need to actually calculate J alpha, that is Lyman alpha flux. Okay, so this is this J alpha. This is actually a spherically averaged number of Lyman alpha photons. So let me write it actually spherically averaged. Spherically averaged number of Lyman alpha photons striking each area, which is denoted as TA, per unit frequency, per unit time, and per unit polynomial. So this is how we define the alpha. This equation. So this equation actually is a bit long. I have this note for 4-5 pages note, and if you, I can give you that one. So I'm not going to discuss that. It's a long calculation. It will take longer time. So I prefer to skip that, but I have a note and you can take it. I can circulate to everyone. Okay, so this is how it is written. Now, in order to calculate this, uh, you have to connect this number to the source property, like uh, properties how sources are emitting, and we need to connect that with that. Okay, so so source properties, the particular quantity that we need to connect these numbers is called source emissivity, ongoing photon emissivity, epsilon. This is called ongoing photon emissivity. So this is basically number of photons. This is number of photons emitted by sources at redshift z per co-moving unit, per co-moving volume per unit time. Okay. So this is number of sources, number of photons emitted per unit co-moving volume per unit time per unit frequency at the next frame of uh, uh, the atom. Okay, so we need to this is something related to the source properties, and this will actually it will produce some diagonal photon diagram. So we need, so from source model we can calculate that, and I will tell you how to calculate that, and we need to establish the relation between this and that. Okay, so again we have to use some knowledge of relative transfer. So let me explain that. So let's consider an area of a surface with of area dA, and we also consider small solid angle through which line of photons are passing through. Okay, and this solid angle is d omega. So how do we define J alpha? So let's consider another quantity J nu that is slightly different from, that is not spherically average quantity, that is same quantity but to a small solid angle d omega. So number of photons that is striking in this that is striking per unit area, is striking per unit area, per unit time, per unit frequency, and per unit solid angle. So that is how we define this spherically averaged laminar flux. Right. So basically, number of photons passing through this area, per unit area, through the solid angle d omega, per unit time, per unit frequency range, solid angle. That is how we define here. Now, if we consider this, so this photon will at some, if we consider time dt, it will cross some length. So it is just c dt. In time dt, it will cross path of c dt. Okay. Now, in CDT time, how many photons that will be added to that? So there is this dn, that is, let's say, now if we use the definition of moving photon emissivity, that is nu and z, and that is so this is the definition of moving photon emissivity, that is EVC and DT D. So this is co-moving volume DC. So this C denotes co-moving volume per unit. So this is defined as number of photons per unit moving volume, per unit time, per unit frequency. Yes. So these two quantities are same. So if we just equate them, so if we equate them, then we get so this term. Before I equate them, let me write EVC, that is moving volume. Moving volume is related to physical volume, dV. How it is 1 plus Z cube, right? So moving volume is 1 plus Z cube multiplied by the physical volume. So that you all know, right? And so 1 plus Z, and then we also calculate the volume, that is area dA and dT, right? So this volume of this cylinder, area multiplied by the distance it covers in distance. So if I put it here, we get 1 plus Z cube dA, and then you will have one more dt CDT, right? So if I equate these two things, we can cancel this term dA dA dt dt d omega d nu d nu. So what is left is essentially J nu d omega is equal to epsilon and then 1 plus epsilon nu z 1 plus z cube e and dt. Okay. So this is how these two quantities are connected. Now, ultimately, we want to calculate the spherically averaged Lyman alpha flux. So, spherically averaged Lyman alpha flux, J alpha. It is also. No, so there are two DT. So, a spherically averaged Lyman flux can be defined as 1 by 4 pi J nu d omega. So we now, instead of considering on small solid angle, we are considering the we are taking average over all solid angle and dividing by the total solid angle. So that's how we calculate spherically average. Okay. So and that will be essentially if I replace this here, so you will get 4 pi epsilon nu z 1 plus z cube c dt, right? So basically J alpha spherically average quantity is this. Now we need to make one small changes. So we know this dt So dt can be written as dt. So we are changing the variable dt in terms of dz, and you know how to do that. So this is simply dz 1 plus z each z. I think you know what is this comes from Hubble formula. Okay, so if you just put everything together, J alpha becomes 1 by, we can take the factor C out of the integration, and then epsilon mu z, and then you have 1 plus z cube, and then you have 1 plus z gap, so it will be 1 plus z square. 1 plus z square, and then dz, and then we also have each z coming from this converse. So this is how we connect moving source emissivity with the linear path. Okay, and this is the formula you will see in your literature. Now there are more stories in that. Which actually is introduced to you. Let me try to understand that in more detail. So actually, this actually gives you. Now what happens? So we want to calculate Lagrange flux at redshift change. However, let's say photon at z prime, which is greater than z. So this is the redshift of our interest. The photons which are emitting at z prime, they will be redshifted to Lagrange alpha at z. So you have to consider those photons as well. Okay. Now, so let's say if you consider photons very close to Lyman beta, corresponding to Lyman beta, so we can calculate the maximum redshift that we should consider like in this integration. So this integration is our z. So lower side is z, but z we have to integrate up to some maximum z. And if we go beyond z max, the photons will be redshifted up to below Lyman alpha, and those are not useful. So we can go up to z max. How to calculate z max? Very simple. 1 plus z max by 1 plus z, that is the redshift of interest, is equal to is basically mu corresponding to Lyman beta by mu corresponding to Lyman alpha. So we know frequency of this, we can easily calculate z max given z. So we need to integrate up to z max. From this equation we can calculate. Fine? Is it fine to everyone? Okay. Now so this is for the Lyman alpha. This is for Lyman alpha, Lyman beta band. But you have photons frequency higher than that as well, right? Now how do you consider that in your calculation? So now you have to understand one more thing, that which actually it is introduced and explained a bit. But let's look at that issue. So you have this, if you remember hydrogen energy level. So this is n equal to 1, 2, 3, 4, 5. Okay. Now consider photons in between Lyman beta and Lyman gamma. Now these photons, so let's say in this case, these photons are emitting at some redshift time, which is greater than z. Now this photon, this Lyman alpha, Lyman gamma photons, or any photon in between this will be redshifted to first to Lyman beta at some at Z. So we are considering those photons which will be redshifted to Lyman beta at Z. Okay. Once it reaches Lyman beta at Z, because this is the resonance frequency, it will excite one ground state atom to actually n equal to 2 state. Lyman beta, it will absorb this ground state atom will absorb one Lyman beta atom and go to this state. And now there are actually so this now what happens to this excited state? Either it will come back again to directly come back to the ground state and produce Lyman beta, one more Lyman beta photons. That is one possibility. But but that possibility is not interesting because it is absorbing all Lyman photon and by decaying it is giving Lyman beta photon. That is not interesting because it is not helping to contribute in the Lyman beta. The next possibility is that it can come down to two states. It can cascade down to n equal to 2. Now see, when they are going to 1 to 3, actually it is going to 3p state because of the selection rule. Because it is one state, one H state. State is always one state, and selection rule is delta L is plus minus 1. No other selection rule are possible. So it will go to 3p state. It will not go to 3s state because then delta L will be 0. It will not go to 3d state because then delta L will be plus 2. So it will only go to 3p state. Now while cascading down, it can come down to either 2s state because 3p to 2s is possible, and but 3p to 2p is not possible because then again this selection rule happens. So it will come back to 2s state. Okay. Now remember it is said that 2s to 1s transition is forbidden transition because again this selection rule thing comes into this. So this transition 2s to 1s is kind of forbidden. But now there is one possibility which is called two photon decay. Extremely low probability possibility that there will be some metastable state and atom will jump to that metastable state first and then again one S state. But that will not produce Lyman alpha. That photon will be gone from the system. It will not contribute Lyman alpha. Right. So that's why as this person said, you asked why you did not consider Lyman beta, Lyman gamma band, because those photons are actually not contributing to Lyman alpha background. So that's why they are not calculated. I mean, you can still write, but the probability that one Lyman beta absorption will produce Lyman gamma absorption will produce Lyman alpha is 0. Okay. Okay, but if you consider Lyman, what is the next? Like epsilon. What is the corresponding? Alpha, beta, gamma, then delta. Okay, so delta. And then Lyman, delta, and then next. But these photons. So let's say you have a photon in this range on Lyman gamma photon, but that is not interesting because it is not contributing to the Lyman alpha background. Second possibility is that it can cascade down. Now this 4p state can cascade down to basically 3s state and 3d state, right? And 3s state can cascade down to 2p state. Right now, this photon actually can contribute to. Now, once it is in 2p state, uh, it can come down to 1s state, which is highly probable transition. But in some cases, photon can end up in 2s state as well. Some photon can end up in 2s state as well. If that is the case, then that photon actually that state will eventually come to 1s state, but with extremely low possibility, and through two photon decay. And two photon decay means no liminal, so it is not contributing to the liminal character. Okay, so that is the keeping this background in mind. What we have to do in this equation, like so, now we have to actually change this equation slightly. We have to sum over all bands n from n equal to 2 to sum n max. So this, for each n, it corresponds to one band. For example, n equal to 2 corresponds to Lyman alpha, Lyman beta band. N equal to 3 corresponds to Lyman beta, Lyman gamma band. N equal to 4 corresponds to Lyman gamma, Lyman delta band. And for each band, there is a finite. Not all photons will become Lyman alpha. Some of them will become. So there is a efficiency parameter called F recycle. So you have to also add F recycle. F recycle. So that is F recycle, and then I can take this factor out of the summation. So this is the full formula. Okay. So you have to calculate for each band separately, and for each band Z max is different, right? So this N max is actually Z max is actually function of N, right? Because how do we calculate Z max? So 1 plus Z max by 1 plus Z is equal to mean Lyman, let's say I plus 1 or N plus 1 by Lyman N. And this ratio is different for different bands. So Z max will be different for different bands. So you have to carefully calculate that, and then you have to take sum of this. And that will give you the total Lyman alpha value. Now you may wonder why I have written N max. N can be invincible, right? Why some example? That's because as you increase N, your Z max, and if you increase N, your Z max and it will become very close to Z actually. As you increase Z, you can calculate it. So if you increase Z, actually these two numbers will be same. So that means the region. So let's say you are here. You are considering lateral photons from. So this is Z axis. This is Z axis. So you are at Z, and Z is increasing in this side. So for the first Lyman alpha, Lyman beta band, this is the Z max. Now if you go to very high end, your Z max will be actually extremely small, very small region. Eventually it will go inside the ionized regions. So once you have a source, it will create ionized regions, which are some value. So typically, so Z max, if you choose Z max, once it is going inside that ionized region, then you stop. Okay. And it turns out that Z max is observed of 23. So if you take sum over 23, it will give you almost correct range. Okay, so this is how we calculate laminar flux. Okay, so now I'll talk about this, how to calculate it.
Cycle is a function of n.
If free cycle is a function of n, so there is a table given in program at the paper. So typically, uh, for the first band, for the laminar for laminar beta, it is around 0.8, and for the next band it is 0 because this orbital thing, and after that it becomes 0.36. So 1/3 of photon actually eventually converts into laminar, and 2/3 photon is gone through these two lines.
We can get max things.
Z max. So this Z max is arising because you are actually including photons which have frequency higher than laminar, right? So let's say I can give you an example, then you will understand. Okay, so Lyman alpha frequency is 1216 angstrom, right? Lyman beta is 1026 angstrom. Lyman gamma is 972 angstrom. So you have a table for this. Now see, let's say there is a photon emitting at this wavelength, a little bit less than this wavelength. This wavelength will increase. It will so let's say I'm at redshift. I'm at redshift 10, and photon coming from redshift higher than 10. Let's say some 10 prime. Those photons will be redshifted, and it will become exactly laminar alpha. How do you calculate the Z max? So you can calculate it 1 plus Z max, because change of frequency is proportional to 1 plus Z, right? 1 plus so new Lyman alpha, new Lyman beta, Lyman alpha. So you can calculate frequency from this number, and that turns out to be this ratio turns out to be 1.18 for this band. Now if you use Z equal to 10, you will get Z max value. That is for Lyman beta, Lyman alpha. If you consider Lyman gamma, Lyman beta, the number will be different. So for different band, the number is different. Okay. Okay. Now we need to calculate this emissivity, source emissivity. So source emissivity epsilon nu z. So there are many ways, but the one that I follow is you can calculate it from mass function. So mass function what is mass function? Mass function actually gives you number of dark matter halo, number density of dark matter halo, moving number density of dark matter halo in the mass range of m and m plus n. Okay, so this is denoted as m. This is mass function. So moving number density of dark matter halo in the mass range of n plus dm at redshift z. That is mass function. And there are some many functional forms given by various people. The one which is very popular, given by Set and Torment. So you might have heard about it. Set Torment mass function, and that can be written. You can actually calculate it. That can be so rho 0 bar m f sigma so that is you can calculate. So rho is present day matter density, mass is yellow mass. F sigma is the mass fluctuations, dark matter mass fluctuations, right? RMS mass fluctuations of dark matter density field corresponding to scale m. So I guess you know how to calculate different topic. So this is the formula by which you can calculate. Now you can actually this. So this is basically dark. So this actually gives you this quantity actually gives you number density of dark matter, moving number density of dark matter in the mass range of n and n plus k. Now if I multiply with n, it gives me the mass density of dark matter in the mass range of n and n plus k. Okay, and then so this is dark matter mass. Inside dark matter mass, inside dark matter halo. Okay, not in the intergalactic medium. This is total dark matter mass inside the dark matter halo. In the mass range of n and n plus k. If I want to calculate what is the mass density, baryonic mass density. So this is dark matter mass density. If I want to convert it into baryonic mass density, I have to multiply with this parameter omega b by omega n, omega b by omega n. The ratio is the ratio of dark baryonic density and dark matter density. So this, if I multiply this factor with this, it will give me the baryonic matter density in the mass range of n and n plus m at redshift z. Now, out of this amount of baryon, some fraction which is denoted by m star, some fraction will be converted into stars. Not all, some of the baryon is converted into stars, and that fraction is called f star. And in principle, it can be function of m and j, but in practice, it is assumed to be constant. Okay, so that gives you. Yeah, so that gives you total amount of stellar mass. So this is dark matter mass, and this factor converts into baryonic mass, and this converts into stellar mass. Now, if I want to calculate the rate at which the stellar mass is increasing, I have to take derivative with time. So that gives you rate of change of stellar mass, of course, per unit volume. Okay, and then we have to actually we need to know the photon distribution. Like so, this is stellar rate of change of stellar mass, but all those stars are emitting photons at different frequencies. So we have to multiply. So if you want to know the spectrum of photons emitting from a dark matter, we have to multiply this with a spectral index quantity. So spectral quantity, and that is epsilon p nu. So you can take any form. So if it is a black body, you know the how it is changing with frequency, right? And if it is not black body, if it follows the power law, you have to assume some power law to the power alpha. You have a very for alpha. And then this we also divide by total mass, because if I divide by the total mass, this quantity will give you it will give me the baryon numbers. So stellar mass, and it is made of baryons. So if I divide by total mass, it will give me the total number of baryons, rate of change of baryons. So this spectral index is written in terms of that. So this is how we calculate. This is how we calculate source emissivity. So what does it tell you? It gives you it gives you number of photons emitted per unit forming volume per unit time. Okay. And if once you calculate it, you just plug that in this equation, and that will give you. Yeah. So there are few steps that you have to follow before you get this number, and once you get this number, yeah, alpha. Once you get x alpha, you can plug in this spin. You get this spin temperature. So there are many processes, but we have discussed the steps that we should follow, and that is exactly is done, particularly in this global signal calculus. Okay. So this actually this particular part, this particular part is also known as star formation rate density. You might have heard about star formation rate density. Star formation rate density. SFRD. In short, it is SFRD. And you might have seen many plots of this as a function of rate. This is one of the most important quantity that people try to model, and also try to compare their model with observations. So this is something you can also infer from your observations. You can model your star formation rate density, and you can actually compare that and extract some parameters. The way that DBs has discussed, like inferences. Okay, is it okay? Any question up to this point? No? Okay. Okay. So now let's discuss one more topic, that is let's focus on the properties of sources. So those are the objects that are responsible for reionization and cosmic breathing. So let's try to model those things. There are several ways. I will follow one which is very simple, and then we can follow. So So by sources we mean stars. Stars are the ones which are emitting photons and ionizing here H1. Also, it is heating up the intergalactic medium and also responsible for laminar path. So there can be different types of sources. Let me write two of them. Pop 2 and pop 3. So that is population 3 stars and population 2 stars. So population 3, these are the stars. They were formed first time in the universe. These are the very first generation of stars, although they are named 3 because we're counting from the present stars. So population 3 stars, and then population 2. So population 3 stars. So how do you form stars? So what do you mean by star formation? So from I think basic stellar physics course you know that when what happens inside the star. Basically, hydrogen atoms fuse with each other and it emits energy, and that is what we call star. So inside star you have fusion going on, and how that process triggers, you need certain condition to actually start that fusion. You need extremely high density, you need extremely high temperature to start that fusion process. Okay. So initially, when you have this H1 cloud and no sources, so now if you consider one H1 cloud which is slightly of higher density compared to the background universe density, then this will actually sink to their center of mass due to the gravitational pull. They will sink, and once they sink due to the gravity, its temperature, density of course it will rise, temperature will also rise. Both density and temperature both will rise. Okay. Now once the temperature of the system is rising, there will be outward pull due to pressure because you have gas, hydrogen gas. So there will be outward pressure. That pressure will go up once you try to sink that cloud further. Eventually, that outward pressure will balance the inward gravitational pull, and in principle, this further sinking will stop. Now you need some mechanism to actually reduce the pressure, outward pressure, the gas pressure. And how can you reduce it? You have to reduce the temperature. So you need some cooling material. Which can take away some amount of heat from the system, and that will allow this cloud to sink further. Now, at present, the efficient cooling material is heavy material. Material which are very heavy. Metals are very efficient cooling, so they can actually. So if you have some metal inside this cloud, so those metals will actually absorb some photons, and they will those metals will be ionized and it will get out from the system, and that's how we can take out. That's how we can take out some energy, or you can take out some heat energy from the system. But at very high density, when the first stars are forming, there are no metals because metals are produced during supernova, and so supernova is the end product of stars. So now first stars are forming, so there is no question of supernova before that. So then, what could be the possible cooling agent? So the cooling agent is at this age. So these metals are not there. So one other possibility is that molecular hydrogen cooling. So you have atomic hydrogen. You can also have molecular hydrogen as well during these initial stages of star formation. Now this hydrogen molecules, they are actually they can dissociate themselves, so they can absorb some photons and they can dissociate themselves and uh, leave the system, right? So these H2 molecules, by dissociating themselves, can take out some heat from the from this cloud, can reduce the temperature further. So this molecular cooling is very efficient. It is really very efficient, although there is no robust evidence of molecular cooling yet at that energy. So this channel can be very efficient, and they will allow to sink this cloud further, and it will allow to trigger the first star formation. So these are the first generation of stars, population 3 stars. And because of this molecular cooling, these stars are very massive. That means it can be of the order of 100 solar mass or even more, maybe 500 solar mass. That is the value. And of course, it is metal core stars. Metal core stars, because of the simple reason that there are no metals before that. Okay. So these are the sources which really were formed during past generation stars. And then once they are formed, since they are very massive, their lifetime is very short. So they will actually end their life very quickly, in about 5-6 years. Now once they are this generation of stars are they die, they will end their life through supernova. Some of them will end their life through supernova. Then after that there will be some metals in that medium, because they will produce metals when they go through supernova. Now those metals can serve as cooling material for the next generation of star formation, and that is called population 3 stars. Sorry, population 2 stars, second generation of stars. And another point is that this is feedback state. Like once you form stars, those stars are emitting radiation, all kinds of radiation, and the radiation which is belongs to Lyman-Warner band. Lyman-Warner band. So that corresponding frequency is so that is 11.2 to 13.6 electron volt. So photon in between this energy range, and they are called Lyman-Warner band photons. Those Lyman-Warner band photons actually dissociate this molecular hydrogen. So molecular hydrogens are the one which are helping to form stars. They are the one which help to form these stars. But the photon from that stars actually dissociating them, and actually it is acting as negative feedback. So because of this, Lyman photons are dissociated and they are destroyed. So now if you do not have this H2 cooling, H2 material, then there will be no cooling channel for this. So after some time, it is believed that these stars will be gone, because you do not have H2. They are dissociated. They are destroyed through this Lyman-Warner band. So initially we start with population 3, but after some time this generation star will vanish from the system, and then this population 2 type star will take over. Okay, that is the second generation of stars, and they are the one which are actually deriving the reionization process, cosmic dawn process.
There is a difference.
No, so this cooling channel for this cooling channel is H2. And for this population 2 type stars, their cooling channel is defined, that is atomic cooling. We have hydrogen atoms, and this atom can it can actually so one 13.6 electron volt photon or higher energy photon can dissociate these atoms, right? And by that way, you can actually take out some photons, very high energy photons from the system, and you can cool off the system. So, but this atomic cooling channel, so in order to make this channel efficient, you need to have very massive sources, massive values, because you need temperature around 10 to the power 4 Kelvin. The system temperature should be at least 10 to the power 4 Kelvin in order to make this process efficient. These are basically polygonal ionization. Now, initially you have small sources. So initially you do not have very massive sources, very small sources. And for those sources, you have this H2 cooling important. Okay. So yes, they are producing Lyman water back and they self-destructing. Yes, and these are also they also produce Lyman. Yeah, so that's why they are very, I mean, you don't see them at present. So maybe so they were formed very early and after that they are gone. They are all gone. So actually we have calculated like how long they can survive. So maybe in the next class I will show, maybe during tutorial I will show you some plots like how Prof 3 star formation rate are decreasing with decreasing rate 6, and Prof 2 star formation rate are increasing. So this 13.6 is basically ionizing photon, and 11.2 it corresponds to this Lyman Warner belongs to this band, but I don't know the significance of this number.
So why is it happening that this self-destruction?
No, so these photons are actually destroying this H2. So H2 have this H1. I don't know the exact process. I prefer to believe that there is a bonding between two H atoms, and that bond is broken if you meet H2 atom through some photons. So they are dissociated. Any further question? Yeah.
Also, there is metal.
Yeah, so metal can also cool. Yeah, both of them. But atomic cooling is not efficient during the first phase because values are small and temperature is very small. So they are not very. Any further question? Okay, so then I will stop now. So tomorrow I will also continue. There is one more lecture tomorrow morning, and then the day after. So tomorrow I will also